Hello everybody. So today we are going to talk about Wavelet Filterbanks. Previously, in our last lecture, we were talking about filterbanks. So we learned how to design and how to use a perfect reconstruction filter bank. A few weeks before that, we learned something about wavelet transforms. And our today's goal is to connect the two topics. So we are going to talk about wavelet filter banks, which is a kind of a special case of decimated filter banks that we have already learned how to design them. Moreover, we are going to define wavelet and scale function with a dirty goal to find a way how to fastly compute discrete wavelet transform. Most of the job will actually be transferred to a digital computer instead of an analog filter bank. And finally, all that effort will result in some beautiful applications of wavelet filter banks and wavelet transforms. So let's start. At the beginning, we are going to recall ourselves that we learned how to design filter banks, decimated filter banks, that still have that property of perfect reconstruction. So the question is, most of the time we were talking about two-channel filter banks, and the question is, do we have a way to use it for a fast realization of octave discrete wavelet transform? Or probably for the definition of the discrete wavelet transform of the discrete signals. So let's start with some kind of the optical resemblance between that analog structure and what we had when we were talking about the filter banks. So right there you can see analog filters that are actually used for the realization of the octave discrete wavelet transform. So what we had was kind of a filter bank with two filters, let's say high pass and low pass filter, and they were fed with an analog signal, so they were analog filters. But we continued the decomposition with an additional set of high pass and low pass still analog filters. And the decomposition went on and on in the low pass branch. So we were already discussing it. Okay, and the outputs of these filters were sequentially sampled. The sampling rate was not the same at all levels. So we had the fastest sampling rate right here, 2 times slower right here, 2 times slower right here, and we can go on and on with such an analysis. When we were talking about such an analog filter bank, we made a kind of a comparison with a piano. So if this corresponds to the highest octave on a piano, then this corresponds to the nearby lower octave, and we can go on and on up to 10 octaves that actually exist on the piano keyboard. But the whole octave is represented only with a single output, single sequence of numbers right now. So the numbers start right here. Okay, that was the story about discrete wavelet transform. So actually I just recall that discrete wavelet transform is discrete only in the transform domain. Everything else is pretty continuous. The signal applied to its input, as well as all the filters in the chain. Okay, so let us use some kind of a physical resemblance. So in our previous lecture we learned how to design something completely different but look alike. It was a set of discrete filters. So here we had a sequence of numbers, okay, where n was an integer. Then we decimated the output of those filters, and we learned how to reconstruct it perfectly in spite of the decimation. Okay, but it looks pretty much the same, except these are the analog filters and these are discrete filters, or let's say it is kind of software, but right here it's pretty much some analog hardware. So how to make a relation between the two? Let's go on with the optical resemblance. Let's go this way. So maybe I can just cascade those filters in a similar fashion. So we will see where it is heading. Okay, I'm gonna continue to decompose the low pass branch. So if this is a low pass branch, let's go on. Let's go and apply actually the same filters. Notice that they do not work at the same rate. So here we have a pretty fast rate of the original sequence of numbers, and here, due to decimation, we have only half of the rate. So these two filters are working on half of the rate, and our plan is to do the decimation again, okay, and again. We have a two-channel filter bank, so the decimation is by a factor of 2, and let's recall that we are talking about some maximally decimated two-channel filter banks. So at least sampling rate corresponds to what we had in this analog filter bank. So here the sampling rate was double than here, which was double than here, and the same thing applies here in our discrete case. Still, we have some missing link between the two. So let's develop it, and it's gonna take some time. We call it a wavelet tree because of its optical resemblance to that filter bank tree that actually realizes discrete wavelet transform. So we always continue with our analysis, with our decomposition in a low pass branch. Okay, since we are not going to use any H and L filters but the special ones, so we can count on the fact that we have a 4 of filters that ensures that the perfect reconstruction is possible. So if we have so we know that there exist some other filters. Which if they were fed by the output of these two channels, they will bring back our signal X to its output. So we are calling that a perfect reconstruction property. So our plan is, if we use it everywhere, for example, if we use it right here, we can reconstruct the signal that comes here. Maybe I can just make a sketch of it without drawing the filters, only the branches. So if we decompose our signal in 2 branches, and then again and again, we can continue, of course, with the story, but let's stop right here for the sake of an example. We always can apply the reconstruction part of the filter bank. Okay, I'm gonna use another color for it to collect it together and to reconstruct what was here. Then we can do it again. So from these 2 channels, that one is just being reconstructed, we can collect the results and we can reconstruct what was here, and now we can apply the same pair of reconstruction filters to get a completely perfect reconstruction structure. So that's not a question. The question is, does it have any connection with the real wavelets? Okay, but if we learned how to have 4 filters that actually provide the perfect reconstruction, it is easy to understand that such a structure will have the perfect reconstruction property as well. So we can always think about this part like being the transform domain, and this is the original signal domain. And here, so this is a kind of analysis part, or so we go from the signal domain to the transfer domain, and then this is a reconstruction part. So we go from transfer domain back to signal domain. Of course, our plan is to do some processing right here, so that is going to come at the end of the story. So let's draw it on the slide a little bit better than my drawing right here. So on the other side we have that part. Okay, so I'm just going to use the same description like on slides. So instead of L, I'm going to use H0 for the low pass, H1 for the high pass filter. So H1, H0, H1, H0. And here we are going to use G. So we were using F, but it's all the same. Okay. This one is low pass and this one is high pass. Maybe we can start to write down some expressions. I'm gonna clear some place right here, so I will show you what is my plan. I have cleaned the light board and redrawn my filter bank, but right now it's in Z domain. So what we have right here, so what is the question? The question is actually which decomposition functions we have and how to bring it in relation with the real analog wavelet filter bank. So what is bothering us? It is a cascade of linear filters and decimators. So maybe it is a good plan somehow to split between the two. Let's have an equivalent cascade of the linear filters, which is easy for analysis and understanding. And then we can split, let's say, the decimator part. We can just push it towards the transform domain, to the last step of our decomposition. So our plan is somehow to move that decimators through the linear filters from its input side to its output side. What is going to help us is called noble identities. We can see them in its general form, so we can move a decimator which is actually applied before the input of a linear system to its output. In that case, the transfer function is being changed. The special case for the decimation by a factor of 2, which is actually our case, is written there. So we can just check it out on right here on the board. So what are we going to use? Let's start. Okay, maybe I can just draw it right here. So our claim is that this guy, h of z squared, followed by decimation, is equivalent or the same as if we had a first decimation, then linear filtering. Maybe I can use the same notation. So we are talking about this guy and this guy. We can see it right here, and we think that we can transfer this decimator through the linear system on its right hand side using the noble identity. Let's check it out. So what we have already learned is the behavior of the decimator. So if we apply any signal to a decimator on the right hand side, on the output of that decimator, what we get is 1/2 of x and z to the power of 1/2 plus x of minus z to the power of 1/2. So that's something that we have already learned. But in our case, at the input of the decimator, we have something that is some x is passing through a linear system, which is actually h0 z squared. Okay, let's write it down right here on the left hand side. So we have actually a product of the two. So instead of having this, we have x times. Okay, and on the right hand side we have to apply this expression, but of course on this argument. So instead of x, I have to write x at h0. Let's do it. So on the right hand side I have 1/2 of okay, and now here I have, it's z squared, and this is z to the power of 1/2, which means that h0 is what remains. And then we have a second term, okay, x minus z to the power of 1/2, but when it is squared, the minus disappears. And what we have, I mean, at least if we are talking about h0, but not right here. So we have x z to the minus, sorry. So squaring of minus and z to the power of 1/2 gives H0 of Z. We can see that this term is equal in both terms, so we can just extract it. And what we have is 1/2 times H0 of Z. We can see easily that this term corresponds to what we had at the beginning. So it's decimated x of z, and then followed by the transfer function. So it corresponds, these two terms corresponds to the right hand side, and the beginning corresponds to the left hand side. So we have just proved the noble identity for the decimation by the factor of 2. I challenge you so you can prove the general case for yourself. We are just going to use this result because we have a third plan to move this decimator near the transformation domain. So symbolically, I'm going to move this to the right. Nothing really changes right here. Okay, I just moved it. But if I want to move this decimator through the linear system, through the linear filter H1 or H0, I have to apply the noble identity. So if I do that, if I move it to the right hand side or to the output of this linear filter, it is going to be z squared. Let's do that. Okay, I'm moving it. I'm moving it through the filter. So right here, I'm going to have squared. Good. I did it right here as well. Squared. How do I know that I move it? So right now the decimator is applied to the output side. We can say that we have a cascade of the two decimators, one that was here before and now the one that passed through the linear system. But if I have a cascade of the two decimators by the factor of 2, I can just draw it as a single one with the decimation factor of 4. And right here I have a guy that is decimation by 4. Now everything is correct, at least in this level of decomposition, but let's go on. Okay, now I have a plan to move this decimator through the linear system onto his output side. So what is going to be the consequence? Okay, I'm gonna move it. This time I'm gonna put it right here. So 4 and 2, it is decimation by 8. But something happens right in here and right in here. So right now it is z to the power of 4 and z to the power of 4. So our goal, we have fulfilled our goal. We made a split between linear filtering and some non-linear signal-dependent decimation. So that was our goal. Okay, maybe we can just write down the equations. So what we have now. At the first level of decomposition, maybe we can just denote the levels. So here is the first level, 1. Here is the second level of decomposition. Here is the third level of decomposition, and so on. Okay, at the first level of decomposition, we have applied only unchanged high-pass filter, so we can just write it down. So at the first level of decomposition, we have H1. That was what we have applied. So the impulse response of such a filter will be something that corresponds with the analysis function applied to that sequence of numbers, that digital signal. Okay, so at the level 2, what we have? At the level 2, this is, let's say, the level 2 of decomposition. That was the level 1. Here is the level 2. We have high pass and low pass branch. So let's write down at first the high pass branch. So we are going to write here the high pass branch. So it's a cascade of 2 linear systems. The first one is low pass, unchanged. The second one is the high pass filter, changed, because here the argument is z squared. Okay then, what we have in the low pass branch, we have a cascade of 2 low pass filters. One is unchanged, the other one is changed. It is z squared and its argument. Let's go on. So let's write down the equations for the third branch. In our third branch, we have a cascade of 2 low pass filters. The first one is unchanged. The second one is changed. And the third one is our high pass filter, changed as well. Okay, we have no space for the next branch, but still we can write down the equations. So it starts from H0, it goes to H0 z squared, then H0 z to the power of 4, and then what is following would be the high pass filter H1 z to the power of 8. It would be somewhere there if we had some space. So how does it look like? It's a kind of a pyramid. In this pyramid, you notice that we have a cascade of low pass filters, and only at the end of the cascade we can see the high pass filter. So it's almost the same like here. So we had a cascade of analog low pass filters at the end of some stage. So we had the high pass filter, and then followed by subsampling. Here we had decimation. So the high pass filters were here, 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 and here. If we were talking about the low pass branch, in that case we would have only the cascade of low pass filters, like also a triangular structure. Okay, let's put it in some equations. So for the low pass branch, we have a, for example, this is number 1, okay, and then level 2. Level 2 is a cascade of 2 filters, level 3 is a cascade of 3 low pass filters, and here we have a z to the power of 1, we can say. So we can say that this is the power of 1. We can say that this is the power of 2. 4 is actually 2 to the power of 2. And 8 is 2 to the power of 3. Or we can start from 2 to the power of 0, which is the same as 1. Now we can see the rule. So if we are talking about the low pass branch, we have only cascade of low pass filters. And if we are talking about the high pass branch, the high pass filter applies only at the end. So let's see the results. So we have a product of such a low pass filters and the low pass branch. Okay, here it is. I can just cover this for the moment. And if we are talking about the high pass branch, then at the very last moment I just apply the high pass filter as follows. So of course this is the third one, and z to the power of 4, which means 2 to the power of 2, so 1 less. So in our product the index goes to capital N minus 2 if we are talking about the high pass branch, and it goes to the N minus 1 if we are talking about the low pass branch. N, of course, is the actual number of the decomposition levels. Okay, so now we are kind of prepared. Maybe it doesn't look very enlightening. Let's wait a bit, but still it is only a product of the transfer functions. It's only a cascade of linear filters. So we can just continue our analysis before applying the decimators, and we can just discuss, is there any relation between the two? Actually, we should have emphasized that these filters are not the same. So these filters were kind of H1, then H2, H3 and L3. So we started from two filters that split the frequency band in two. Then we had some more selective filters, probably of higher order, to split it again and again and again till the last octave of our analysis. Right here we were using actually the same filters in all decomposition levels, but due to decimation they also changed. I can easily see that the overall effect of that cascade is not the same. What happened is that z squared, z to the power of 4, z to the power of 8 in argument of our function. So the right question is, what does it mean? What does it mean when you say that you have h of z squared or z to the power of 4? What kind of a filter it is? Let's discuss it a little bit later. I cleaned some space on the light board, so we have enough place to make an example. So somehow these product of functions will correspond to something that we call wavelet function. And if we are talking just about the other branch, low pass branch, in that case we are going to talk about some complementary decomposition function that is called scale function. So we can easily see that the two channels are somehow complementary. So half of the information goes one side and the other half on the other side. Okay, so let's see an example. So my example on the board will be pretty simple. So when we were talking about two-channel filter banks, let's say the simplest possible high-pass filter was something like this, 1 and minus 1. That was H1 of n, the impulse response. I'm going to use unscaled version, so it's 1 and minus 1. And when we were talking about the low-pass branch, the impulse response was pretty simple, only two ones. 1, 1. So actually the output of the low-pass filter was average, okay, the scaled average of the input sequence, and the output of the high-pass filter, the simplest possible, was only the difference between the two neighboring samples. So that's what we had. Okay, so now we have the product in Z domain or in frequency domain corresponds to the convolution in and the time domain. But still we have that problem, which is actually, what does it mean, Z to the power of 2? Okay, let's go to the Z domain. So H1 of Z equals 1 minus Z to the minus 1. And okay, H0 of Z, each sample corresponds to one term in the Z domain, is 1 plus. Okay, very simple. Okay, let's just rewrite it using square. H1 Z squared means that wherever we see Z on the right hand side, we have to put Z squared in. So the result is 1 minus Z squared to the power of minus 1 is Z to the power of minus 2. And the other guy, low pass guy, looks like this. Let's make some drawings in time domain. So in time domain it looks like so that one remains at the same place, and now we had a minus 1 right here, but now it's right there. And the other one looks like this. Instead of having it right on the place 1, it's now in place 2. Actually, it looks like somebody has inserted zeros in between the samples. So if we say that if we have in Z domain Z squared, it corresponds to inserting zeros in between the samples. If we have 0 to the power of 4, it's only inserting more zeros. So H1 to the Z power of 4 is equal to 1 minus Z to minus, so 4 minus 4. Or if we are talking about the low pass filter, it's the same but with plus. So more zeros in between, 3 zeros in between 2 samples. I still have some place right here, or maybe I can just draw it. One, 2, 3, and then 1. If we are talking about the high pass filter, or 1, then 3 zeros, nothing before the z to the power of -4. So 3 zeros inserted in between the samples. So it is something that is very, very simple. So the powers, the higher powers of z correspond to inserting zeros. In French, it's called a trou, which means with zeros. So these filters are actually the filters with inserted zeros in their impulse responses. The number of non-zero samples remains the same. So this guy, and this guy, I mean, this guy has higher order than this guy, this guy, but what we have is only, in our example, if this guy had 2 samples, 2 non-zero samples, this guy also had 2 non-zero samples, this guy also had 2 non-zero samples, and so forth. So let's say the calculation burden does not increase. It remains the same. So squaring or powers in z domain, I'm talking about the argument of the function, corresponds to inserting zeros and does not bring any new burden. Okay, so let's create these filters. Let us see them. So the first one is 1 up, 1 down. Okay. The other guy is the convolution of 1 and 1 with 1, 0, -1. Okay, this guy is right here. So the convolution of 1, 1 and this guy, what do I have to do? How to convolve? I have to mirror it. It's pretty invisible in this case because 1 and 1 still remains 1 and 1. So I slide over this signal, and what I got is 2 1s and 2 -1s. Okay then, let's go to the level 3 of decomposition. Now I have a cascade of 2 low-pass filters. This guy, it's always right here, and this guy, it's right there. So convolution of this guy and this guy will give us something that looks like this: 1 and 1 and 1 and 1. Okay, and it is still to be convolved with h1 to the power of 4 with this guy, and the result is 1, 2, 3, 4, followed with 1, 2, 3, 4, and so forth. The next level would be 8 ones followed by 8 minus 1, 2, 3, 4, 6 ones. all the time it looks the same. We can even imagine that it is a kind of sampling of a continuous function. It has never happened, of course, but we can always imagine that there is a continuous function that looks like this, that looks like this, or like this. And the biggest one, and actually what we had as a cascade of a completely discrete filters is nothing else but the sampled version of that wavelet functions. So a careful observer noticed that I'm talking in this example about the Haar wavelet, and it really corresponds to a very, very simple discrete wavelet filter bank in the sense we have just discussed. And some more complex examples we can see on slides. Instead of starting from such a simple filters, we can start from some other pair of filters that we have already learned how to design. So our first example is DB2, which is Debussy 2 filter, and that's what happens when we cascade the filters. So on the left hand side you can see the cascade of low pass filters. So we are right here and here and here and one level more. And on the right hand side, in the right hand column, you can see what happens in the high pass on the high pass side. So actually these are the samples of the impulse response of H1, and then cascade of one low pass filter and high pass filter with inserted zeros gives the other level. The interesting thing is that we have an impression. I mean, these functions are not the same. I mean, this is not the same as this one, as this one, as this one, but as the level of decomposition increases, we can see that approximately the number of samples doubles. It was exactly in this Haar case, but down there it's not exactly, it's only approximately, it doubles. And optically it looks the same. So that's something that we can always imagine, that there exists some kind of a continuous function which samples are down there. And in our more complex example, it's not exactly the same function. It becomes the same as the number of the level of decomposition tends to infinity. But when we go backwards to the first level of decomposition, it's a little bit different than the second level of the decomposition, and on. So we feel that it could be a good approximation of wavelets. In the Haar case, it's a kind of a perfect, it's still, we have an impression that it's going to be a perfect approximation of the continuous wavelets. Still, we have something to do before we can declare our victory. At first, we are going to define some kind of a helpers function. How does it look like? Our helpers function will be, each sample we are just going to, with a magic wand, we are going to transfer it to a continuous function. So let each sample corresponds to a piecewise approximation of a continuous function. in that case, we are going to have what we had. So our continuous wavelet functions by collecting it together. But there is also one more thing to do. So in the first level of decomposition, we will say that this corresponds to 0, and this corresponds to, okay, I can say 1 in my example. You will see it's going to be a little bit different on the slides, 1. But also I can say that here I have 0 and 1. Here I can have 0 and 1, 0 and 1. In that case, I can clearly see that it is only a one function that is actually expanded or stretched. So it's expanded or stretched by the factor of 2. In our example, it is an exact stretching or expansion. In case of other wavelets, I can easily say wavelets now, it's going to be an approximation which is better and better as we go, as our level of decomposition goes to infinity. So what we define, it's a kind of a piecewise constant function. We have split it in how many pieces? It depends how many samples we have. So if we have capital N is the number of samples, in that case we split it and we can just draw the result. So let's draw the result, then when you go back to that equations you will find out what are we talking about. So we are talking about the piecewise approximation of decomposition functions, and all of them are equally scaled. In my example it was 1, in example on slides it was corresponding to the initial number of samples of these functions, so it was like 4. So right now it's easier to see that we have some kind of optical resemblance between that functions. We can, looking from the bottom up, we can say that we are looking at the same thing, let's say in lower and lower resolution, with less and less precision, something like that. So, but if we are going to the bottom and on to more levels of decomposition, the result will be something that looks exactly the same. On the left hand side, in the left hand column, we can see we can see scales, the outputs of the low pass filter, and on the right hand side you can see wavelet functions, the outputs of actually the high pass filters. Outputs of the high pass filters are actually what are we looking at, and the other outputs are kind of helping functions. So scale is a kind of a helping functions that helps in the construction of the other side of high pass side, which corresponds to the wavelets. So if we do the same story on the reconstruction side, which is not drawn here on the light board, we can have something very similar. So let's go one slide before, one slide on, before, previous, next, previous, next. You can easily see that in this particular case the functions are mirrored. So once again, previous, next, previous, and next. So the analysis functions are kind of mirrored reconstruction functions, and you will learn soon that we are talking about an orthogonal filter bank. Associated piecewise constant function, converge when the decomposition level goes to infinity, or even sooner in some special cases. If the resulting functions are successfully smooth, we can say regular, in that case it is going to be pretty useful for many applications. So in transform domain here or here, we will have some desired result, which is useful for compression, for storage, for feature extraction, or some other type of some other application. So convergence and regularity of associated wavelet and scale functions. Now we can define what is the wavelet and scale function. It is that associated function when the decomposition level tends to infinity. So it is an associated and imaginary continuous functions that it is in the background of our samples and of our discrete system. We learned how to design orthogonal or biorthogonal filter banks with some perfect reconstruction property. Are they all going to give us nice wavelet filter banks? The answer is no. Only some of them will result in the functions that converge when the number of levels of decomposition tends to infinity. So what is, we will not prove it, we are just telling the story about it. What kind of conditions must satisfy these filters to expect that the result will converge? So we expect that the low-pass filter has a zero at the Nyquist frequency. So it is kind of necessary. If you don't, fortunately, all the methods we were talking about the design of our filter banks were ensuring that we have a proper amount of zeros at the right place. Actually, I think we need a better explanation for my last claims. So let's start again. I just cleared the glassboard, and let us recall what we have learned about the design of filter banks with the perfect reconstruction property. So we learned how to design filter banks binomial or max flat, actually the ones that have binomial up to the power of 2p. I'm gonna choose some better marker, okay, where p is some integer, okay. And then we needed a helper polynomial. It has been shown that it must be at least 2p minus 2. That was the order of the polynomial to provide the necessary properties for perfect reconstruction. So actually, when we were talking about Haar wavelets, we actually fixed that p to 1. So what we had is 1 times 1 plus z to the minus 1 to the power of 2. Okay, I'm gonna split it in two parts. And that polynomial was of 0 order, and we can still recall that the result was 1/2. We can actually split that 1/2 in two parts, like 1 over square of 2 and 1 over square of 2. So altogether it's 1/2. And then we can split it in two parts, like this, using scissors, to divide the two parts between the two filters. Two filters where I can just put it this way. So we had a low pass branch. I will follow the same notation as in this lecture. So here I'm going to put H0 and here I'm going to put J0. Okay. And the other pair in the second channel was H1. So if this is a low pass branch, this is a high pass branch, H1 and J1. So to provide a perfect reconstruction property, we needed that Q polynomial, which is in this case pretty simple. And in spite of decimation and inserting zeros, we still had that perfect reconstruction property. So we are going to collect it in a wavelet tree, but for now let us just recall that this is an important point. Here we have our wavelet coefficients. And on the other side we have that approximation coefficients, which will be followed in the next level of decomposition. Okay, that was a very simple example. Maybe I can just draw some most important properties of these filters. We can see that one and the other, they are actually the same in our case. They have a 0 at the Nyquist frequency, which is in a way expected. So one can expect that the filter has zeros. The low pass filter has one or more zeros at the Nyquist frequency. So 1 0 goes to H0 filter and the other one goes to a J0. So I'm going to use different colors for that. So our product filter had 2 zeros at the Nyquist frequency. Okay. It was simple. Then we can use some other P, like P equals 2. In that case, we can split it in multiple ways, but one possible solution is definitely that we split it so that binomial part, which is now up to the power of 4, it can be split in many ways, but we can split it in half, for example. So we have square here, square there. And this polynomial is not a constant anymore, it is something more than that, but I'm just going to write down that 4 minus 2 equals 2. It is of order 2, some polynomial. So you can just take a look in our previous lectures to find out what is the exact value of that polynomial. We can still split it in many places, but let us split it right here as before. Now we have to decide which filters are going to be H0 and which one is J0. It is, let's say, it is wiser solution to choose this simpler one for J0. Why? Okay, so let's do the choice. J, and all together it's H0. Why? Because if we want that this system has a perfect reconstruction property, in that case we have that secret connection between J0 and H1. Okay, maybe we can just draw it as well. So we have that secret connection between the two. Actually, H1 is equal to J0, only you have to reverse the signs of every second sample of its impulse response. Maybe we can just write it down. So if this is J0, in that case H1 is 1 minus z to the minus 1 to the power of 2. Something very simple. And of course J1 is equal to minus H0 of minus z. Of course the right hand side has to be put right here. So this guy is very simple. So let's say this filter is a little bit more important in our design because it defines the filter which actually defines our wavelet coefficients. So that's the reason why people take care about the design of J0, because it's indirect way how to design H1, which generates our wavelet coefficients. And the other branch, the other sub channel, is going to another level of decomposition. So this point corresponds to approximation coefficients, which is not so important like our wavelet coefficients. So right now, so we had actually two zeros at the Nyquist frequency for J0 and two zeros for H0. Reversing sign actually means mirroring of zeros. If this belongs to these two zeros, actually belongs to J0, the consequence will be that our H1 filter will have two zeros mirrored on the opposite side. This is a high pass filter and it has two zeros at the DC frequency. So that was about H1. So H1 and J0 are in a secret connection, as well as the opposite. So the green, which actually belongs to H0, is in a secret relation with J1, and J1, due to the fact that H0 has also two zero moments, will have two zeros at the DC frequency. So that was, we have just recalled some facts about design of the Wavelet Filterbanks, and we have discussed the relation between zeros of individual filters in the low pass branch with the zeros of the individual filters and the high pass branch. Of course, in the low pass branch, zeros are set on the Nyquist frequency, while in the high pass branch, zeros are actually situated at the DC frequency. It's gonna be very important when we will discuss the properties of wavelets, and when we finally realize why that kind of transform is good for analysis of real-world signals. So we'll come to that fact again. Now we can just see some more examples. We could, of course, split Q2 also in two parts, and that's what happens while we were using Debussy 2, which was orthogonal. So in that case, even Q2 was split in two parts, and these filters were more, two reciprocal parts, and these two filters were not equal, but they were of equal order. In my example right here, they are not of equal order. Actually, such a choice corresponds to something that is in MATLAB denoted as BIOR, like bi-orthogonal filter bank. So this guy and this guy have two zeros, so J0 and H1, they have two zeros. H1 has two zeros at the DC frequency, and the other filter in this variant has also two zeros. So now I need a green color. So the first number corresponds to the zeros of J0 and H1. The second number corresponds to zeros of H0 and G1, which is, let's say, less important for our wavelet coefficients. So right now we are ready to understand the next slide. So in our next slide we are looking how the analysis functions look alike at the different levels of decomposition. Just time axis is normalized for easier comparison between them. So on the right hand column we can see that the wavelet functions are kind of nice functions. I mean, do not forget that they are actually the product of H1 and previous H0s. So in the very first level it's only three coefficients, so we can see them right here. So here we have a power of 2, so what we expect is 1 minus 2 and 1, so it looks like that. So on the right hand column, the first level. And then the things are getting more and more complex due to H0, which is not so nice, which contains the whole Q2 polynomial. So that BIOR 2.2 means that we have two zeros right here and two zeros right here, as well as vice versa in the high pass branch. Good, but reconstruction functions are much nicer. Look at them. On the left hand side I can see the scale function in different levels of decomposition. Actually they are product of J0s. So at the first level we have, due to this power of 2, we have 1, 2 and 1. Okay, it looks nice. But in the second level, and the third level, fourth level, I mean, they actually gather together forming a triangular scale function. And what happens actually to the wavelet function, I mean the reconstruction one, oh, it's nice as well. So it's a product of nice functions, and it looks kind of very, it has a very nice shape, something like that. Obviously, these wavelets have some good properties for description of the signals, for decomposition of the input signal. If we do something, I mean, the purpose of a filter bank is to do something in the transform domain, not only to reconstruct the original signal. So if we do something with wavelet coefficients, if we change it, if we double it or kill it, the consequences on the reconstructed signals will be shaped as in the rightmost column, depending on which wavelet coefficients we are talking about. So let's say the changes on the reconstructed signal will be a nice shape, which is, if we are talking about decomposition of images, it will be kind of something that we like to see. And the same stands for audio signals as well. Now we are ready for probably the most difficult and most important part of the story about wavelets and filter banks. So we are just about to connect the two roads. Approximately in the first part of our course we were talking about wavelet transforms. So we defined some integral expressions that defines the continuous and discrete wavelet transform. Then we were talking about filter banks, and now it is the time to connect the two stories in a single one. So let's start from a pair of functions, pair of wavelet and scale functions defined as we did it in this lecture, and let them converge. So we will make some examples for easier understanding. So let's have it. Let's have two functions that actually converge. So we can just, I'm going to make an example so we can think that we can start from that hard wavelet transform. It's, let's say, the most simple wavelet and everybody can understand it. So let our psi function be something like this. So here I have 0 and then 1, so that's our psi function. Okay, and now I have to define some scale function which actually corresponds to that wavelet function, and we will see very soon that it is something like this. Actually a rectangular pulse. 0, 1. Okay, I'm gonna put the other values an axis. So 1, 1, and -1. So this is our phi of t. So we are talking about some continuous functions. So we were talking about hard wavelet even before, when we didn't even start to talk about wavelet filter banks. So for the moment, these two functions are continuous, and we can just imagine that they can also be associated with some wavelet and scale functions defined as we did it at the beginning of this lecture. So they They are in the limit sense over many levels of decomposition. They converge and do something like this. Just be patient a little bit so you will see how is it possible. Then we have a claim that in that case we have following relations between scale, wavelet function, and actually filter coefficients of the filters in the bank. Okay, it seems a little bit difficult, but it is, we really do not understand at this moment how it works, but let's just take a look at the expressions. So the expressions are like, okay, filter coefficients, I mean, they are impulse responses. In these equations act as kind of weights in a linear combination of shifted scale and wavelet function of double speed. So we have 2t on the right hand side of both equations. Okay, let's try to make a real example so we will find out how is it possible. Let's check it out. Okay, so that's the claim. If this is the claim, then I must be able to construct on the right hand side my wavelet function as a linear combination of double speed scale functions eventually shifted by an integer value. That's what is written on the right hand side in that equation. Let's do it. So double speed means okay, it's still a pulse but 2 times shorter. Okay, and then I can shift it by some k to the left or right depending on the sign of the k, and I must construct my wavelet function psi of t from as a linear combination of such guys. I can do it. Seems pretty easy. So if I collect 2 guys, one which is shifted by 1 but with minus 1, the coefficient must be minus 1. Okay, so if I sum it up, I'm gonna get my psi of t. So it's possible. Okay, in front of that summation there is a square of 2, so I will probably have to divide this one and this minus 1 with a square of 2 just to fit in that equation. So it's not gonna be 1 or minus 1, but probably 1 over square of 2 minus 1 over square of 2, just to cancel that square of 2 which lives in that right equation. Okay, so it is possible to construct my wavelet function, my Haar function, from 2 double speed scales. On the left hand side I can see that even the scale function can be constructed from its own double speed copies. I mean double speed and shifted copies. Yes, of course it can be. I mean, it's even easier than this. We can see that 5T can be constructed from two guys like this one and this one, where we have 0, 1 half, 1. Again, I mean, the amplitude will not be 1, but 1 over square of 2 to cancel out that square of 2 which lives in our expression. So let's discuss it on the slide. So all the time we are talking about Haar wavelet, and yes, this is the definition of the Haar wavelet. It is 1 over the interval from 0 to 1 half. It is -1 right here and 0 elsewhere. And then we can construct it. My helper scale function, let it be a pulse of the full width, 0 to 1 and 1. And then I can construct it from two guys, the red one and the blue one, from two guys, yellow and red on my light board. And of course I can even construct the scale from two guys. So my coefficients are actually 1 over square of 2 and -1 over square of 2. And of course, so the sum on the right hand side has only two addends, only two. So in general it can have many addends, but in our case it has only two. In case of Haar wavelet it has only two coefficients, and actually these are our coefficients. We have already seen that. And yeah, scale function corresponds actually to another pair of coefficients, 1 over square of 2 and 1 over square of 2. We have already seen that coefficients. Yeah, in this moment I can clearly see that we are talking about Haar filter bank with two filters, H0 and H1, where H0 actually has two coefficients. I'm going to put it this way: 1 plus z to the -1 times 1 over square of 2, and H1 equals 1 minus z to the power of -1 times 1 over square of 2, something that we have already seen. And actually it corresponds to this way of how to construct the wavelet and the scale function. It seems miraculous. So we have a pair of functions, scale and wavelet, and we can construct that wavelet from double speed scales. Is it the only possible way? No, of course not. There are so many other examples. Some of the examples are that if we have such a scale function, like a triangle, we can construct that triangle from its double speed copies, something like this, plus this, plus this, all together gives this, and the associated wavelet function looks like this. it also can be constructed from these guys in a very similar fashion. Okay, my drawing is not so precise, but I think that you can understand the point of my story. Yeah, we have already seen even that. It was my previous example with bi-orthogonal filter 2.2, and something like that we have already seen as a reconstruction, scale and wavelet function. So that's very nice. Still, we need an extra step to connect the two worlds. So what we need is to write down the equations, actually to connect this story with integral formula we have already seen at the beginning of this course. Okay, let's do it together. So we are very close to connect the two worlds. World of wavelet transforms in its integral form and the world of Filterbanks. So let us recall the expression for the discrete wavelet transform. So discrete wavelet transform was described by the following. So we can calculate the wavelet coefficients using the following expression. A0 was some kind of initial scale, so we use the powers of that initial scale and we had that integral form. Actually, the comparison between the signal and some kind of wavelet which is actually shifted and scaled. Scaled and shifted. Okay, so once you choose the initial scale, k as well as the time shift m are integers. So today we are going to explain how to realize octave discrete wavelet transform, which means that we have chosen initial scale equal to 2. It's not going to be enough to analyze music or to find out which tones were in the play, but I mean the A0 equals 2 corresponds to the whole octaves in the piano, for example. But it is pretty good for compression, denoising, and a lot of other applications that actually can be realized using Wavelet Filterbanks. Okay, so if we want a direct implementation of the discrete wavelet transform, we need to calculate a bunch of integrals. Notice once again that the only thing which is actually discrete in discrete wavelet transform is the result, the spectrum, which is calculated on an integer grid. The signal itself, as well as the wavelet, shifted and scaled, is still continuous, and this is a integral form. So it is computationally demanding. You can choose any wavelet function in this integral form, but instead of it, let us use a reduced set of wavelets, the ones that have associated scale function. So we can write it down, let's say, in an alternative form where we just collect together everything that is associated with the wavelet. And in that case, we can use that form from actually from the slide. And now we choose not any wavelet, any admissible wavelet, but only a subset of the wavelets that are actually have that scale function. There are many families of wavelets. For example, in MATLAB Wavelet Toolbox package or some else toolbox like in Python or some others. And you can design some pairs of your own because you learned a lot about filter banks. In that case, my dirty plan is do not calculate this integral not even once. So how is it possible? And I'm going still exactly. I will exactly calculate the wavelet coefficients. How to do that? Instead of integrating with a wavelet function, I'm going to use the scale function. So maybe I can write down an example. So if this is some kind of x of t, for example, the waveform of my voice, I can use some kind of a pair of scale and wavelet function. Har example. So the scale was actually a rectangular pulse, and associated wavelet function was something like this. Okay, so instead of using this and directly calculating wavelet coefficients, I'm going to use a pulse. I'm going to use a pulse in some initial scale, and then I'm going to shift it in different positions, like this one, or this one, or this one, or all of them on some integer shift positions. I'm going to multiply with the function x of t and calculate the result of the integration. Actually, in this very simple case, due to the fact that this is 1, it is only like cutting the original signal in pieces and calculating the integrals. So the first result by multiplying of this guy and this guy will be the area right here. And then the neighboring area, or I can just write it here, this is this area or this area. So it's about integration of the original signal. In fact, a lot of sensors do it by itself, including this camera I'm just looking at. So it is integrating the light over some time interval. It doesn't have to be necessarily 1. I mean, in practice it can be any time period t. It's only about our definition. So instead of this, I'm going to use this. So I start from some initial scale, initial k, and I can define it, let it be 0. So I'm using the scale in its initial form. I'm shifting it all over the time axis, and I just write down the results. I'm gonna give them a name. So since we are starting from the scale k equals 0, the only thing that remains is index m, which corresponds to shifts. And let us name the result. We will call it approximation coefficients at the level 0. So let's call it approximation coefficients. And keep in mind that approximation coefficients in some special cases can be produced by the sensor itself. And let's say in some general case you have something like this. It will, of course, depend on the scale function. In many cases, the scale function is finite, and you are going to need a very simple hardware. So one can say it's like a convolution, but okay, signs are not okay, so probably convolution with the mirrored scale function, and integration over some finite period, and then again some different place which corresponds to time shifts. So either you got it by the sensor itself in our case, or you have to realize some kind of a very simple hardware to get that approximation coefficients. And then what happens then? Then we can calculate all the wavelet coefficients using actually the filter bank. How is it possible? Let us see it together. So at first I have to notice that the wavelet function itself can be expressed as a linear combination of the scales. So maybe I can just clean some space and we can do it together. So, okay. Okay. So, wavelet function itself can be expressed as a linear combination. So we have a sum. It can be a finite sum in many practical cases. So the index goes from 0 to some, let's say, capital N1. In our case, our sum had only 2 addends. And then we had actually filter coefficients H1 multiplied by double speed scale shifted by some shift n. So at first I will recognize that my scale is 2, so I'm gonna clean it and put it right here. Okay, we don't need it anymore. And let us calculate the wavelet coefficients. I mean, we have to start from some scale, so let it be 1. If this is 1, then this k, I can just erase it. So what we have is wavelet function calculated in place t over 2 minus m. Okay then, so what I need is a kind of I have to put t over 2 minus m instead of that t, which means that right here I'm gonna have, okay, 2 times, it's gonna be t minus 2m instead of 2t, and of course minus n remains unchanged. So let's go on with our slide. So since we have this expression, and since for the first level of decomposition we need to calculate this integral form, then I can just put it right here in my integral form. So let's do it together. So I just put it in here. Okay, my next step is to exchange the order of integration and summation. So let's do it together. So I'm going to put the sum first. Still, this sum can have only a few addends. Okay, so what depends poorly on n? Okay, h1. It doesn't have t. And then remains our integral. Okay, here it is. X of t times v calculated in the place t minus n minus 2m. Okay, but we already have that results. I mean, we have already calculated our approximation coefficients. We call them approximation coefficients at the level 0. They came from the sensor itself or from some very simple hardware. And the only thing we have to write it down. So these are actually already calculated approximation coefficients, not at the places m, but at the places a, 2m plus n at the level 0. Okay then. Instead of m, we put n plus 2m, 2m plus n as follows from this expression. Okay. Finally, we have a simple sum with h1 impulse response of a filter and some coefficients coming in. We can recognize that this is a discrete convolution. Okay, or it should be a discrete convolution. The only thing is that discrete convolution over n, which disappears from the equation finally, and the result is over m, like we needed. But it is a wrong sign. And we have that 2m, which means that we calculate only every second result. Okay, altogether it corresponds to filtering, so filtering of these coefficients using H1 filter, okay, which is mirrored, so minus is missing, and which is actually decimated, followed by a decimation by the factor of 2, so we only need every second sample of the result. We have already seen that. So that's a part of our Wavelet Filterbank. So there we had an input, we had a filter H1, and we had a decimation by the factor of 2. Only the input was unnamed. Now we are going to put the approximation coefficients at the level 0 right here to get our wavelet coefficients at the level 1. So that was the level 1. What's next? Notice that even the scale function is a linear combination of its double speed scales. So we can completely repeat that procedure in a very similar fashion using H0 and M2. So using the other expression that we have already discussed. So our second expression explains that in our case we can calculate the scale, we can express the scale as a linear combination of its double speed copies, shifted copies. Actually it corresponds to the other filter, H0, and after decimation, using the very similar procedure, we can get the approximation coefficients. If this was 0 scale, here we are going to have the scale 1, and this corresponds to wavelets at the level 1. And now we can go on and on. We can continue our analysis right here. We can use the same filters right here to calculate the next scale, the next approximation coefficients, and the next level of the wavelet coefficients. So we just arrived to our goal. So it corresponds to filtering and decimation. So we have a procedure how to fastly calculate discrete wavelet transform. Of course, octave discrete wavelet transform, so our scale was 2. So at first we integrate our signal multiplied by the scale functions and we calculate the integrals only once. Or in practice it will be probably served by the sensor itself or some very simple hardware. Then, once we have it, we can just feed the wavelet tree to calculate all the remaining coefficients without the need for direct implementation of this integral form. So it just arrives from the wavelet filter bank. Notice that at each level we have only n operations, order of n operations, where n is the order of these filters. It is kind of extremely efficient numerical realization of the wavelet transform, and that's the main reason why is it used, except for its good properties, why is it used in many applications like digital video, like the video you are just looking at, in analysis of audio signals, extraction of the features that are useful for some subsequent processing or machine learning or some other applications. So wavelet filter bank can be used for a fast computation of the octave discrete wavelet transform. Not only for that, since we learned how to design wavelet filter banks, we have a powerful tool for design of novel pairs of wavelets and scales. So it is a filter bank's design of the filter bank is also a method of design of orthogonal or biorthogonal wavelets. So altogether we are going to show some nice applications of wavelets. So let's see how it behaves when let us calculate wavelet coefficients for some choices of that pairs of wavelet functions and scale functions. Let's start. Let our signal be two sine waves, two sines of different frequencies. So it is in the leftmost column, the first one. Actually, the decomposition starts from the bottom up. So let's say the bottom row corresponds to D1 and A1 coefficients. As you can see, D1 is almost empty. There is nothing here. If we put two signs right here, we have a lot of zeros in details and the wavelet coefficients of the first level of decomposition. So if we had 1000 samples right here, we have 500 samples right here that are almost zero everywhere except for one place in the middle where the two signs are connected, where there is a kind of a discontinuity in the signal. On the left of the left-hand side, you can see the approximation coefficients, and they actually are looking like a subsampled original signal. That's why we call it approximation coefficients. It's a kind of a approximation of the original signal, but of the lower resolution. So we have only 500 coefficients right here. Then we go on with A1. So from the bottom, it's the second row from the bottom. Now we can see that there are a little bit more details right here, but still a lot of them are equal to zero. So we go on and on and on. And finally, we have, let's say, 250 coefficients, then 125, then 64, 32, and 16 coefficients. And let's say details in the right column shows actually our wavelet spectrum of the observed phenomenon. We can see that it is almost everywhere it is zero. The used wavelet was Debussy-4, which is an orthogonal wavelet with 4 zeros on H0 filter had 4 zeros at the Nyquist frequency. If you choose, if the filters have more symmetry in its impulse response, it is a little bit better description in the wavelet domain. And finally, if we use Haar wavelet, like in my example, we are going to get some kind of the reverse Gibbs phenomenon. So I believe that most of you are familiar with the Gibbs phenomenon. So that was the story about actually Fourier series. If you want to describe the rectangular periodic signal, using sine waves, actually you need a lot of sine waves to properly describe the edges. And so on. Finally, so we need to add a lot of signs to properly describe that discontinuities. In this part, it converges fast, but on discontinuities, it converges slow. In this example, we have a reverse situation. We want to describe signs using Haar wavelets that are actually rectangular. And still we have the same property. We need a lot of rectangular wavelets to properly describe sine waves, and we can see that the description in the wavelet domain, in the Haar wavelet domain, is not sparse. Actually, it corresponds to the Gibbs, to reverse Gibbs phenomenon, as we know from signals and systems and some other courses. So probably it's not the best idea to decompose sine waves using the Haar wavelet transform. Okay, but still, if we are using discrete wavelet transform, if we apply it to real-world signals, what happens is the coefficients are almost everywhere zero. The representation or the wavelet spectrum is very, very sparse, very compact. So the information is somehow concentrated. How is it possible? So let's start with some different signals, like polynomials. So if we apply the wavelet transform to a signal which is actually composed of polynomials, which is polynomials on intervals, in that case, what we are going to get is, in the wavelet domain, it is going to be zeroed almost everywhere except on the edges of that intervals. So let's make an example before writing down any expressions. So in our example, we are going to use the bi or 2.2 wavelet. What does it mean? It means that it followed up from a wavelet filter bank. I'm going to write it down. I'm going to draw the wavelet filter bank. Okay. And in different color, the different pair of filters. Okay, so that was our wavelet filter bank. So when designing the filter bank, at first we talk about the product filter. So low pass branch, low pass band. We were talking about these two guys, and the choice 2.2 means. It means that number 2 corresponds to zeros of this filter. Okay, I'm gonna draw it, and this is the z-plane, unit circle. Okay, 1. And this guy has 2 zeros right here. Another 2 means that even this guy has 2 zeros in this place, which is not so important. What is important are zeros actually of this filter. Why? Because there is a secret connection between the two. So if this guy has 2 zeros right here, this guy is going to have 2 zeros right here. And that is important property, that is an important fact for vanishing polynomials. So that's why we call it a vanishing moment, but we will come to that fact later. So let's try it. Let's apply this wavelet to something that is actually composed of 2 polynomials. In our example, it's going to be 2 lines. 2 polynomials of the first order. So lines are polynomials. So the first row represents the signal itself. It is composed of two lines, but the difference between the two lines is so small that we cannot even see that by the naked eye. So let's do some wavelet decomposition using Bayer 2.2 wavelets. So we have a wavelet tree. Okay. We start, so on the slide we have D1 coefficients on the bottom, in the bottom row, then one upper row is D2, then D3, D4, we have even D5, and the rest is A5 approximation coefficients. So from the bottom up we can see D1, D2, D3, D4, D5 and the remaining approximation coefficients A5. What we can see that they are almost everywhere zero. So if we had, let's say, 1024 coefficients right here, it's halved from each level to another, and they are almost everywhere zeros except where two lines are connected together, except in the place that we have that discontinuity. So we can see that wavelets are good for detection of that discontinuities, and they are also good for the compression of information, because in the wavelet domain among these there are many zeros. Only a few coefficients are different from zero, actually, in the place of discontinuities. How is it possible? Well, is it always like that, or why that polynomials did not pass right here? So what was the reason of that? So let's go on and let's try to explain that phenomenon. So if this filters has zeros right here on the Nyquist frequency, which means that the frequency right here is equal to pi, in that case the associated H1 filter has zeros at the DC frequency. It has two zeros right here. Okay, one zero kills DC. What happens with two zeros? Probably they kill the lines. Let's see why it happens. So if the filter has a 1 0 at the Nyquist frequency, it means that no signal of that frequency can pass through this filter. The claim is, let's see the claim and then we will prove it on another slide. So the claim is that having zeros at the Nyquist frequency means that this filter is not going is going to kill signals of that form, -1 to the power of n times n to the power of j. Let's prove it. So if the filter has, in our example, two zeros at the Nyquist frequency, what does it mean? It means that h of 0 equals 0 at that frequency, of course, but also we have two zeros, but also derivative of h0 will be also 0 at the Nyquist frequency. If we had more zeros, if here we had 3 or 4 or 5, in that case all of them will be 0. So not only the frequency response, but its derivative, first derivative, second derivative, and so on, up to 1 less than m, which is actually the number of this guy, is m. So the number of zeros right here is m. Okay. Let us write it down. Let us write it down, the expressions for the frequency response, how to calculate the frequency response of that filter. So we calculate it as, so we just write down the expression for the Fourier transform, and that expression contains, okay, I just used h, so I'm going to continue with this. So if I just put that omega equals pi, then I have e to the j pi of n, and altogether this is minus 1. So it is minus 1 to n if I just put the Nyquist frequency in my expression. Okay, now I can derive its expression over omega. Omega is only right here. So derivative of the exponential function is the exponential function itself, only that omega goes out. And when I put pi right here, what I'm going to get is jn minus jn in my expression. I can go on and on to the second derivative, to the third derivative, but if my filter is designed in such a way that this filter have zeros at the Nyquist frequency, then all of them will be equal to 0. If I just equate these expressions to 0, what I'm going to get is exactly the claim from the previous slide. So that's it. So all that expressions will be 0, up to the number of zeros that this filter has at the Nyquist frequency. So once we learned how to design such a filters, and we said it is probably good to put some zeros on the Nyquist frequency, now we are going to learn that why is it good? Zeros right here corresponds, I'm going back to the previous slide. Okay, so in the previous slide we had that expression. So we are talking about this filter, okay. So on the board it's G, so I'm going to put G equals 0. So it equals 0 for such a, so I can just write here n to the power of j, and j can be 0, 1, 2, 3, of course depending on how many zeros the filter has at the Nyquist frequency. My filter has 2 zeros, so it will work for 0 and 1. It will work so actually we have 2 expressions. In my case, I can say where n to the power of 0 is invisible, and n times is also equal to 0. If we had more zeros, then I could write down more such equations, and everything stands for this filter. Okay, how about this filter, H1? What is the secret connection between the two? Oh, that secret connection is right here. I'm gonna just move that and let's say to the right, okay. And I can recognize that this guy is nothing else but H1. So multiplying by -1 to the power of n means to reverse sign of every second sample of the impulse response, and that was the secret connection between the two. So that was the reason why it is important for this filter to have some good properties, to have zeros at the Nyquist frequency, because it produces zeros at the DC frequency for the H1 filter, which we can see right here. And so let's write it down so we can recognize that -1 to the power of n times f0n is nothing else but my filter H1. Okay, and finally I have a final result that n in general, n to the power of j times H1 of n equals 0. What does it mean if j, in my example, j is 2, or the maximum j is 2? What does it mean? It means that if the input sequence right here was all ones or all constant, it's actually n to the power of 0, and it doesn't go through the filter H1, it cancels it out, so the result is all zeros. Okay, but I could put n times constant, it looks like this. It's actually a line. That was exactly my example. Okay, it also doesn't go through this filter, it cancels it out because j can be 1 in my example. Okay, n times H1 is still 0. So the polynomials in discrete domain can be expressed as a linear combination of n to the power of 0 times some constant plus n to the power of 1 times some constant term. Then it could be, I mean, it's not in my example, but it could be kn or j, n to the power of j, and so on. So this is a general expression for the polynomial, for the discrete polynomial. It is composed of such terms, and if m was greater than the biggest polynomial term, the biggest power in polynomial terms, they will all be zeroed. So nothing passes through this high-pass filter. So that's the reason why polynomials die. They are kind of eaten by the filter bank and nothing passes through. Okay, but we have a perfect reconstruction filter bank, so information is not lost. What if my signal is composed of the polynomials? How is it possible to do the perfect reconstruction? Of course, the information goes through another, through the low-pass filters and goes from one level to another. The decimators reduce the number of the samples, so the information is more and more concentrated until it can be described as polynomial. Nothing goes to the wavelet spectrum. So that's why wavelets are kind of information compressors, so they can squeeze information in only a few coefficients if the signal was a polynomial. But most of the real-time signals, images, volumes can be locally described as polynomials. If we were talking about the continuous continuous wavelet function, in that case we can write down the expression, the integral expression that looks like this. It's called a moment of a function. So if the moments disappear, we say that we call it vanishing moments. So that's why we are talking often about vanishing moments of the wavelet functions, not always about zeros of the individual filters. So we are talking about vanishing moments and the polynomial annihilation property. So wavelets are ethers of the polynomials, nothing passes through. If the wavelet function has m vanishing moments, it means that mth order polynomial is not going to pass through. Wavelet coefficients will be all equal to 0. That's a good property. Wavelet decomposition annihilate polynomials, and most of some regular functions, most of the functions from the real world locally can be represented by or at least approximated by the polynomials, and nothing remains, so the information is going to be pretty much compressed, and description in the wavelet domain is going to be very sparse. Only a few coefficients will be different from 0, as we have seen in our example. So that was a pretty good property. So because most of the signals of interest can be locally described as polynomials. Which signals cannot be described as polynomials? What is the opposite of, let's say, order, law and order? Let's say the opposite of the law and order is a chaos, and the signals that cannot be locally described as polynomials are, for example, white noise is one such an example. Let's try to decompose a white noise using some orthogonal wavelets. If we feed a wavelet tree of some orthonormal wavelets using white noise, what we expect, actually white noise will remain noise in the coefficients. If the wavelet was orthonormal, if it preserves energy, actually in all wavelet levels we are going to have still a noise of approximately the same amplitude. So let us see the example. The first row, the red one, corresponds to original white noise. Then from the bottom up we can see the first level decomposition, the second level decomposition, and so on, and they are almost the same magnitude, so the white noise actually spread over all wavelet coefficients. On the contrary, the polynomial-like signals are information is kind of concentrated in only a few wavelet coefficients. It gives us a very good idea how to split between the noise and the signal, how to split between information and disinformation. If, after wavelet analysis, the noise is spread all over the coefficients and the signal is actually concentrated in only a few coefficients, one idea is to let's see the idea. To kill the small ones. So if the polynomial part is kind of zeroed and it only lives in approximation coefficients, or discontinuities are described with large spikes, then it is good to set a threshold, and that threshold divides let's say the two: information from disinformation, the signal from noise, but in the wavelet domain. So if we kill the coefficients lower than some threshold, it's called hard thresholding. If we kill them and then let's say decrease the other by the absolute value of that threshold, in that case we call it soft thresholding. Let's see both examples. So once we have this corresponds to hard thresholding, so killing the small ones. And what we are actually doing, we are in wavelet domain, we are doing a non-linear operation on wavelet coefficients. So we are killing the small ones and leaving the big ones unchanged. You can see the sketch on the right hand side and the equation on the left hand side. And what is soft thresholding? Soft thresholding is just reducing the size of the big ones by the amount of the threshold, so we do not have jumps, let's say, in amplitudes of the coefficients. It is more appropriate to human observer, to our ear or our eye, but let's say hard thresholding results in lower square error or better signal to noise ratio. So how to choose appropriate threshold? I mean, there are many papers that are dedicated to the choice of the proper threshold. A lot of statistics is in there, but still I can say that if you have let's say a Gaussian distribution of the noise, you can just start from, let's say, if this is 2 or 3 sigma, most of the noise is right here. If you use orthonormal wavelet Filterbanks, so the amplitudes are not changed, and choosing the threshold, which is actually proportional to the deviation of the noise, is a good idea. That k can be a number between 1, 2, or 3 if we just talk about the noise, how to kill the noise. But of course it has to be less than the magnitude of the signal description in the wavelet domain. So we always choose that k in such a way to preserve most of the signal and to kill most of the noise. So all of that methods, after many pages and many mathematical proofs, will finally result in some k, which is a number between 1 and 3. So you can even try to put some number and to see the results. So if something suits your needs, it's going to be okay. So hard thresholding does not change the energy of the signal, and if you finally compare, if you apply some signal to noise ratio measure, it's going to get better results. But soft thresholding is often better for the human observer. We can say one word more. If you just abandon these decimators, what you are going to get, it is a quite redundant decomposition, but it gives you can of course continue your decomposition in the low pass branch. Just take care that you have to apply filters with zeros, with inserted zeros, when you go to the next level and to the next level. And if you do it properly, and if you apply the thresholds, you're going to get a little bit better results with non-decimated filter banks. So let's see some examples. In the first row you can see some signal which is actually with some noise added. So on the left hand side in the column from the bottom up you can see the wavelet coefficients, and after application of the threshold in the wavelet domain you can see the results in the right on the right hand side column, also from the bottom up. And the reconstruction gives the signal which is significantly better, so the edges are still preserved. That's what we wanted. The edges were resulted in high wavelet coefficients, and they are almost unchanged after the non-linear operation of thresholding in the wavelet domain, and the signal is reconstructed. Some can say we can do low pass filtering. Yeah, on the left hand side you can see the results. A5 is actually a low pass filtered result, but then you don't have that sharp edges as you have when you apply denoising in the wavelet domain. So that was a straightforward application. This can show how to denoise some chirp signal which changes the frequency, and also you can see that it works pretty fine. It can, except for these examples, there are many more, like wavelet regression, estimation of the probability density functions in wavelet domain, and it is a widespread application of wavelets in denoising, as well as in compression. For the compression, let's say, it's almost, the principles are almost the same, because the information is concentrated in only a few coefficients. So by itself, you have a lot of zeros and only a few coefficients, and then if you can code them efficiently, if you spend your bits in a proper way, then the compression ratios can be significantly better than using some other methods. So that's why it's used in digital cinema or JPEG 2000 standard and some other standards of compression. So we can just take a look at some results. This is the estimation of the probability density function, or some kind of wavelet-based regression. We will not discuss it in detail, we just show the results. I believe that with your knowledge of wavelets and filter banks you can reproduce some of that results on your own. So this is the list of the topics we have discussed in this lecture. We mentioned images, but images are two-dimensional signals. So until now we were just discussing the wavelets and wavelet filter banks that can be applied to one-dimensional signals. So how to apply the wavelet transform to two-dimensional signals? Many of very useful applications such as digital cinema are definitely two-dimensional, even three-dimensional if we take into the account the time axis. So what happens with images? Or volumes. So one possible way how to apply the wavelets or wavelet filter banks to two or more dimensional signals is separable wavelets. What does it mean? It means that we apply the filters into each possible dimension. So I'm gonna start with illustration of an image. Image is a two-dimensional entity. It consists of rows and columns. So I'm just going to illustrate a couple of rows, and definitely it has some columns. So one possible way, so the separable way, is to treat each row as a one-dimensional signal. So what we do is the following. So we apply a filter bank, wavelet filter bank, which consists of two filters in the bank. Okay. To each row of an image. So it consists of two filters, and I'm gonna put some description right here, like H0 is the low pass filter and H1 is a high pass filter. And to distinguish between the rows and the columns, I'm gonna add an additional sign. So we apply it horizontally. So filters as well as the decimators are applied horizontally. Okay. What happens? If we do it at every row of the image, the result will be actually two images of half the width. So the result will be, after application of this filter bank, it's gonna be two images with the same number of rows. Okay, I'm not going to write it down. With the same number of rows. But half of the width due to decimation in horizontal direction. So one of them will be high pass filtered in horizontal direction, and one of them will be low pass filtered, of course, in the horizontal direction. And what happens next? At the next stage, we apply the same filters but across the columns. So let's write it down. So now we are using columns. So columns are one-dimensional signals again, and we are applying the same set of filters, H1, H0, and again H1 and H0, as well as the decimators, but this time it happens in vertical direction. So to make a distinction between the first stage, I'm gonna add the letter V everywhere. So the four filters, two pairs of filters, were applied in a vertical direction as well as the decimators. So the result is that each of these half images will be additionally split, and the result is actually four images of quarter of the size of the original image. When I say quarter, it's approximately. It always depends on the length of these filters, so I'm just ignoring it for the moment. So if we are applying hard wavelet, in that case, it's going to be exactly 1/4 of the original image. And we need some, let's say, some more explanation. So we can notice that one branch is low pass in horizontal direction, followed by low pass filter in the vertical direction. So it's low pass, low pass. I'm going to write right here low pass, low pass. The opposite of it is a high pass filter in both directions. So let's put it here, and in the middle we have a combination. Low pass filter in horizontal direction followed by a high pass filter in the vertical direction. So we can just put it here. We can collect it all together and actually present our result also as a novel image. What we expect that low pass corresponds to our approximation coefficients. So this is the place where we go on with the next level, decomposition. So notice that in each and every level, actually we had 4 points. So we split a two-dimensional image into the 4 sub-images, and only low pass goes on. So we continue our decomposition and the next level. So again, the low pass goes on, and so forth. Notice that the same can be applied to any number of dimensions. So it can be applied to 3-dimensional signals, 4-dimensional signals, or whatever we want. It is not the only way how we can generalize one-dimensional wavelets to multiple dimensions, but this is a very practical one, the simplest one, so one can easily use it. So if we just illustrate it again, so we can see that in the first level of decomposition, the original image is split in 4 sub-images. Low pass is on the bottom right, so it's a kind of approximation, an image which is actually very similar to the original one but in lower resolution, and our decomposition goes on. The rest are called details or wavelet coefficients. Now we have 3 groups of wavelet coefficients: high, low, and high-low. And actually each of them represents a part of the spectrum. So it's easy to see that high pass corresponds to the outer parts of this two-dimensional spectrum. And let's say that mixed parts corresponds to some orientations like diagonal or something like that. So much about multidimensional wavelets.